where trains just float on air and, revolutionary diagnostic tools become way cheaper, much more accessible. That's really the extraordinary promise of high-temperature superconductivity. It's a scientific field that was, well, utterly transformed by just one really audacious experiment.
Yeah.
So in this deep dive, our mission is to extract the most important nuggets of knowledge from the sources you've shared with us, helping you understand what makes these materials just so extraordinary, why they were so darn hard to find, and frankly, why they're still pretty challenging to work with.
And what's particularly striking about this whole story is, how often major scientific breakthroughs really come from thinking entirely outside the established box.
Right.
Before 1986, superconductivity, it was considered almost a mature field, confined to extreme cold, like really extreme. This discovery didn't just nudge a boundary. It fundamentally changed our understanding and just blew open the possibilities for practical applications.
Okay, so let's unpack this a bit. Before 1986, the world of superconductivity was, pretty well defined ever since its discovery way back in 1911 by Kamerlingons.
A huge moment.
The leading explanation for how it worked was the Bardeen-Cooper-Schrieffer theory, BCS.
BCS, yeah. The gold standard.
And this theory explained how certain metals could get to zero electrical resistance at temperatures just, a few degrees above absolute zero. That's incredibly cold.
Minus 273 Celsius, basically.
Yeah, and for over a decade, the record for superconductivity had been stuck. 23.3 Kelvin in a niobium-germanium alloy. That was back in 1973. It really seemed like we'd hit some kind of theoretical wall.
Precisely. The hunt for new superconductors was, largely confined to conventional metals, intermetallic compounds.
Right.
The prevailing wisdom was basically that we were bumping up against the ceiling of what was even possible with those kinds of materials.
But then you get Georg Bednorz and K. Müller over at IBM Zurich, and they did something, really counterintuitive. Müller apparently had this long-standing interest in perovskite ceramics.
Which is odd, right? Because ceramics.
Exactly. Ceramics are generally known as electrical insulators. They don't conduct electricity. So to even look for superconductivity in these materials, that was a deeply, deeply audacious move.
We're a long shot.
Yet after years of really methodical work, in early 1986, Bednorz saw it, a sharp drop in resistance, around 35 Kelvin. In this specific ceramic compound, lanthanum, barium, copper, and oxygen, LBCO, they call it.
Yep, LBCO.
And that was an astonishing 12 degrees Celsius higher than the record that had stood for 13 years.
It was huge, but they were cautious. They actually published their findings without full confirmation of the Meissner effect.
Oh, okay.
Which is, definitive proof that active expulsion of a magnetic field. It's the true hallmark of superconductivity.
So initial skepticism, it was high because of the weird material and that relatively high temperature. Right. But here's where the story takes this amazing turn. The simplicity of how they made the ceramic their synthesis method. That was key.
Absolutely crucial.
It meant other labs could jump in and replicate the work really fast. So by the end of 1986, you had groups at the University of Tokyo, University of Houston confirming the discovery. And crucially, providing that missing Meissner effect data.
That was the validation.
And that confirmation just triggered this unprecedented explosion of research. A global scientific race was suddenly on. It all culminated in the March 1987 American Physical Society meeting, which people famously called the Woodstock of Physics.
Oh, yeah, it was legendary. Just madness. Nonstop presentations, new results pouring in.
And just within months of that, Paul Chu's group at Houston synthesized YBCO, yttrium-barium-copper oxide, pushing the critical temperature clear above 90 Kelvin.
90 Kelvin. It was unbelievable. And the Nobel Committee, they saw this extraordinary impact. They awarded Bednorz and Müller the 1987 Nobel Prize in Physics less than 2 years after their paper came out. That's the shortest time ever between a discovery and a Nobel Prize in physics. Just incredible speed.
So beyond that incredible story, what actually is superconductivity? You mentioned the key markers.
Right. It really boils down to two fundamental properties. First, the complete disappearance of electrical resistance below a certain critical temperature, TS.
Zero resistance.
Zero. Which means an electrical current could, in theory, just flow forever with no power loss. Imagine that.
Okay.
Second, and just as important, is the Meissner-Ochsenfeld effect, discovered back in 1933. This is the active expulsion of a magnetic field from inside the material when it goes superconducting.
So it actively pushes it out. It doesn't just, block it.
Exactly. A hypothetical perfect conductor would just trap any field that was already there. But a true superconductor actively kicks it out. It's a thermodynamic signature proving superconductivity is a distinct quantum state of matter. And, that's what allows for those really cool levitation demos you might have seen online. The magnet floating, that's the Meissner effect.
Ah, okay, got it. And these properties, especially now at these much higher temperatures, that just unleashed enormous practical implications, didn't it? Why was crossing that 77 Kelvin mark such a big deal?
77 Kelvin. That's the magic number because it's the boiling point of liquid nitrogen.
Right.
Before 1986, all known superconductors needed liquid helium to work, which boils at a ridiculously cold 4.2 Kelvin.
Okay.
And liquid helium is expensive, it's difficult to handle, and it's actually a finite resource.
Yeah.
Liquid nitrogen, though, it's everywhere in the air, it's cheap, you can condense it easily, and it's far, far easier to manage.
So suddenly, applications seemed possible.
Exactly. This wasn't just, tweaking the numbers. It was a genuine paradigm shift that made commercial applications seem potentially viable, really, for the first time.
From a theory perspective.
Oh, just as revolutionary, maybe more so. The critical temperatures they were seeing, like 35 K, then 90 K, they were considered completely impossible for conventional superconductors, the ones governed by that BCS theory.
Because BCS relied on
electron-phonon interaction. Vibrations in the crystal lattice acting as the glue for electron pairs. These new temperatures strongly signaled that a totally different, unknown mechanism had to be at play. The old rulebook, it seemed, just got thrown out the window.
So the rulebook was the BCS theory. Let's dig into that a bit.
All right, BCS, developed in 1957, Bardeen-Cooper-Schrieffer. Absolutely groundbreaking work, Nobel Prize stuff.
Yeah.
It proposed that electrons, which normally repel each other, could form these things called Cooper pairs.
Pairs.
Through a weak attraction mediated by phonons. Phonons are basically quantized vibrations of the crystal lattice, the atomic structure.
Okay, like sound waves in the crystal.
Sort of, yeah. Think of an electron moving through the material. It slightly pulls the positive atomic cores toward it, creating a little region of positive charge behind it. This deformation, this ripple, then attracts a second electron, so they become indirectly linked, bound into a pair.
Oh.
It is. And the key experimental proof was the isotope effect. If you change the mass of the atoms in the lattice, use a heavier isotope. For example, the vibration frequencies change, and so does the critical temperature, T(N)I)1. It scales in a very specific way. That confirmed that phonons were indeed the glue.
And these pairs then do what?
They condense, all the pairs drop into a single macroscopic quantum state, like a giant coherent wave function across the whole material. And that allows current to flow with absolutely no resistance.
Okay, that theory worked beautifully for decades. But then came the cuprates, these new high-temperature materials.
And they just ignored the rules. It was fascinating and deeply confusing for theorists.
How so? What rules did they break?
Well, first off, the temperature itself. There were calculations, notably by W.L. McMillan back in '68, that put a kind of theoretical upper limit on how high teeny's coop could get if phonons were the glue. Around 28 to 40 Kelvin, this was called the McMillan limit.
And the cuprates?
They just blew right past it. 35 K, then 90 K, eventually over 130 K at ambient pressure. That strongly indicated a much, much stronger pairing mechanism was needed, something beyond phonons.
Okay, temperature was one thing. What else?
Pairing symmetry. BCS predicted a simple, uniform pairing. It's called S-wave symmetry. Think of the energy gap needed to break a Cooper pair. It's the same no matter which direction the electrons are moving.
Like a perfect sphere.
Exactly. But experiments on the cuprates, techniques like Aripes, showed something much more complex, a Dord wave symmetry.
D-wave.
Yeah, it means the pairing was anisotropic. The energy gap wasn't uniform. It actually went down to zero in certain directions, like a four-leaf clover shape instead of a sphere. That's fundamentally different from BCS.
And the isotope effect, the key proof for BCS.
In the best Cuprate superconductors, the optimally doped ones, the isotope effect is really weak, sometimes almost non-existent. That was another major blow to the phonon idea. If phonons aren't the main glue, the isotope effect shouldn't be strong.
So multiple strikes against the old theory.
Oh, yes. And maybe, if you zoom out a bit, perhaps the biggest challenge to BCS is the truly bizarre normal state of these materials, what they're like above their critical temperature.
They're not just normal metals up there.
Not at all. They exhibit what scientists call linear resistivity with temperature. The resistance just goes up in a straight line with temperature, not like the t-squared dependence you see in ordinary metals.
Yeah.
And they have this weird thing called a pseudo-gap.
Pseudo-gap.
It's like a partial gap, a suppression of available electronic states that opens up way above the superconducting temperature, T-SAIR. But it doesn't actually lead to superconductivity itself. It's very strange. This whole strange metal phase points towards something BCS doesn't really handle well. Strong electron correlations, electrons interacting very strongly with each other.
Okay, so BCS is out, or at least incomplete. What started filling the void? What were the new ideas?
Well, the scientific detective story began. And honestly, there's still no single theory that everyone agrees on, which tells you how complex this is. But several prominent ideas emerged, mostly focusing on those strong electron correlations and, crucially, magnetism.
Magnetism. I thought that usually killed superconductivity.
Usually, yes.
Right.
But here's the clue. The parent compounds, the undoped versions of these coprates, they aren't metals at all. They're Mott insulators.
Oh, insulator.
Meaning the electrons repel each other so strongly, they basically get locked in place on the atoms. They can't move easily to conduct electricity. And importantly, these parent compounds are antiferromagnetically ordered. Their electron spins line up in an alternating pattern.
Okay.
Superconductivity only appears when you dope. These insulators add or remove electrons to make charge carriers mobile. This strongly suggests that magnetism, or fluctuations related to it, plays a absolutely central role.
So maybe magnetism is the glue instead of lattice vibrations.
That's one of the leading ideas. Spin-fluctuation-mediated pairing. Instead of exchanging phonons, electrons interact by exchanging magnetic fluctuations, ripples in the magnetic order, sometimes called paramagneons.
And does that fit the evidence?
It actually fits quite well. This magnetic glue naturally favors the D-wave symmetry that's observed experimentally. And experiments like inelastic neutron scattering have seen evidence for these magnetic fluctuations behaving in specific ways when the material becomes superconducting.
Interesting. Any other big contenders?
Oh, yes. Another very influential, though maybe more radical, idea came from P.W. Anderson, the resonating valence bond, or RVB theory. It starts from a picture of a quantum spin liquid. Imagine the electron spins aren't ordered antiferromagnetically, but instead form dynamic, fluctuating pairs singlets constantly rearranging. It's a very exotic quantum state. Anderson proposed that in this state, electrons might even fractionalize into separate entities carrying spinions and charged holons. Doping introduces mobile holons, and their condensation could lead to superconductivity. It's a very different picture, trying to explain that weird normal state too.
Yeah, that sounds pretty mind-bending.
It is, and there are other approaches too, exploring different kinds of electron lattice interactions or things like electronic pneumaticity, where the electronic properties break the crystal symmetry. And of course, huge computational efforts trying to solve models like the Hubbard model that capture these strong correlations. It's a very active, very challenging field.
So it's fair to say high-temperature superconductor isn't just one thing. It's a pretty broad umbrella term.
Absolutely. It covers a diverse range of materials, and likely different mechanisms too. We generally split them into two big families. The unconventional ones, like the cuprates and iron-based ones, where these strong correlations and magnetism seem key.
Right.
And the conventional ones, which are more BCS-like, even if they reach high temperatures under special conditions.
Let's stick with the unconventional ones first. The cuprates were the first, and you said they still hold the ambient pressure record.
They do. Their unifying feature, structurally, is these flat, two-dimensional planes of copper and oxygen atoms, the CuOS planes. That's where the superconducting action happens.
Okay.
These planes are separated by other layers, often called charge reservoir layers, and tweaking those layers is how you control the doping, the number of charge carriers in the copper oxide planes. This layered quasi-2D structure makes them highly anisotropic. Their properties depend strongly on direction.
And you mentioned their evolution, from insulator to superconductor.
Right. The parent compounds are these antiferromagnetic Mott insulators. As you dope them, you suppress that magnetic order and superconductivity emerges. But it's not simple. The critical temperature TC typically follows this characteristic dome shape. Too little doping or too much doping and TC goes down. There's an optimal doping level for the highest TC.
And they have that weird pseudo-gap and D-wave symmetry.
Exactly. Those are hallmarks of the coprates. Key examples. Well, the first was LBCO around 35K, then YBCO hitting 92K, BSCCO went up to about 110K, TBCCO to 125K. And the current ambient pressure record holder is a mercury-based cuprate, HGBCCO, reaching about 134K. There's often a trend where TC peaks with 3 copper oxide layers per unit.
Okay, then after the cuprates came the iron ones, which is weird because iron is usually magnetic and bad for superconductivity.
Right. It was another big surprise. The discovery of iron-based superconductors, the FSCs, in 2008 was huge. because it proved high TC wasn't just some quirk of copper oxides.
So similar structure.
Also layered, yes, but the active layers involve iron and typically an element like arsenic, a pnictogen, or selenium, a chalcogen. Their parent compounds are often poor metals, not insulators like the cuprates, but they do typically have magnetic order, something called a spin density wave, or SDW. Doping, or pressure, suppresses the SDW, and superconductivity appears.
Different symmetry.
Often, yes. The pairing symmetry in iron-based superconductors is frequently found to be different from the cuprates, sometimes described as SINA, which is still unconventional but distinct from D-wave.
And are there other unconventional ones popping up?
Yeah, the field keeps evolving. Nickelates are getting a lot of attention. They're structurally similar to cuprates, and researchers found ways to stabilize them at ambient pressure using clever thin film techniques. We're also seeing superconductivity emerge in strange places, like at the interface between two insulating oxides, or even in carbon-based materials like specially engineered graphene layers.
Okay, so that's the unconventional family. What about the other branch, the conventional BCS-like ones that still reach high temps?
This is the high-pressure frontier. Really fascinating stuff. It was kicked off, theoretically, by Neil Ashcroft decades ago, who predicted that hydrogen-rich compounds, under immense pressure, might mimic metallic hydrogen and become high-temperature superconductors.
And did it work?
Oh boy, did it work. First, hydrogen sulfide, HS, squeezed to 155 gigapascals, that's over 1.5 million times atmospheric pressure, showed superconductivity at 203 Kelvin.
Minus 70 Celsius. That's amazing.
It was. And then came the clathrate superhydrides, things like lanthanum decahydride, LIAR. Under pressures around 170-200 GPa, they hit TC values around 250 to 260 Kelvin.
Whoa, wait. 260 Kelvin? That's like minus 13 Celsius. That's almost room temperature.
Tantalizingly close, isn't it?
Yeah.
Really astonishing results.
But crucially, these are conventional. BCS-like. How?
Yes, that's the consensus. It comes down to hydrogen being extremely light. Light atoms mean very high-frequency lattice vibrations, very high-frequency phonons. In the BCS framework, high-frequency phonons can mediate a very strong pairing interaction, leading to a very high T.
And the isotope effect?
Strong isotope effect observed. If you replace hydrogen with its heavier isotope, deuterium, TC drops significantly, just as BCS predicts for phonon mediation. That's the key evidence.
Any other conventional high TC examples?
Well, there's magnesium diboride, MgB, discovered in 2001. It superconducts at 39 Kelvin. Not as high as the cuprates or hydrides, but still high for a conventional mechanism. It's considered BCS-like, but it's a bit unusual because it has two distinct superconducting energy gaps.
Okay, so wrapping up the materials, it's a real mixed bag. You've got this clear trade-off, it seems.
Exactly. The hydrides give you these incredible near-room temperature TC values, but only under absolutely crushing, impractical pressures.
Right, millions of atmospheres. It's not useful for a power cable.
Not really, no. Then you have the cuprates with high TC, normal atmospheric pressure, which is great, but they are ceramics brittle, difficult to manufacture into usable forms like wires. And the iron-based ones, they tend to be more metallic, maybe easier to work with, but so far their critical temperatures haven't reached the same heights as the best cuprates. So the choice really depends heavily on what you want to do with the superconductor.
Right. So performance isn't just about temperature, is it?
Not at all. Temperature, TC, is just one piece. Superconductivity actually exists within what we call a critical surface. It's defined by three key parameters that are all interdependent.
Okay, what are they?
There's TC, the critical temperature. Then there's JC, the critical current density. That's the maximum electrical current the material can carry per unit area before it loses its superconductivity.
And how much juice it can handle.
Precisely. And finally, HC2, the upper critical magnetic field. That's the maximum external magnetic field the material can withstand before superconductivity is destroyed.
So you need high TC, high JC, and high HC2 for good performance?
Ideally, yes. And they're linked. If you push one parameter close to its limit, the limits for the others often decrease. If you exceed any of these critical values, TC, JC, or HC2, the material suddenly quenches. It instantly reverts back to its normal resistive state, which can be quite dramatic in high-power applications.
I bet. Now, you mentioned something about type I and type II superconductors earlier.
Right. All these high-temperature materials, the cuprates, the iron-based ones, even MgBs, they are type II superconductors.
And the difference is?
Type I superconductors, mostly pure elements found early on, completely expel all magnetic fields up to a certain critical field, HEC. That's the pure Meissner effect. But type II superconductors behave differently. Below the lower critical field, HC1, they expel fields completely. But between HC1 and a much higher upper critical field, HC2, they enter a mixed state.
Mixed state.
Magnetic fields are allowed to penetrate, but only in the form of these discrete quantized tubes of magnetic flux. They're called vortices or fluxons.
Like tiny magnetic whirlpools.
Kind of, yeah. Each vortex has a tiny core of normal, non-superconducting material, surrounded by a circulating supercurrent. But crucially, the bulk of the material between these vortices remains superconducting.
And why is that important?
Because it allows the material to remain superconducting overall, even in the presence of very strong magnetic fields, right up to HC2. This is absolutely essential for building high-field magnets for things like MRI or particle accelerators. Tight biomaterials just can't handle high fields.
Okay, but you mentioned JC, the current limit. How do these vortices affect that?
That's the crucial engineering challenge. Flux pinning. You see, when you run a current through a type 2 superconductor in a magnetic field, that current exerts a force on the vortices, the Lorentz force.
Pushes them sideways.
Exactly. And if these vortices move, that movement causes energy dissipation, which basically means resistance reappears. So a high intrinsic HC2 isn't enough. You need to stop the vortices from moving to achieve a high JC.
How do you stop them?
You need to pin them, trap them in place. And you do that using defects within the material's crystal structure. Things like impurities, grain boundaries, dislocations, even deliberately introduced nanoparticles. These act as sticky spots where the vortex core energy is lowered, making it harder for them to move.
So you actually want some imperfections.
You do. But it's a delicate balancing act. A perfectly pure, defect-free crystal would have terrible JCF because there's nothing to pin the vortices. But too many defects, or the wrong kind, can disrupt the superconductivity itself. And it gets complicated. Grain boundaries in the ceramic cupriates, for instance, often act as weak links. They obstruct the supercurrent flow between grains, severely limiting JC in bulk samples. That's why early YBCO wires weren't great.
And anisotropy, does that play a role?
Big time. Especially in the layered cupriates. JC can be very different depending on whether the current and field are aligned with the crystal layers or perpendicular to them. So optimizing pinning is complex.
Okay, so you have these amazing materials, but they're brittle ceramics, and you need to control defects perfectly to get high current. How on earth do you make a usable wire out of that?
Yeah, that was the billion-dollar question. It really required completely rethinking how you even make a conductor. The solution that emerged, particularly for the cuprates like YBCO or related compounds, REBCO, is what's called a coated conductor, specifically the second generation, or 2G HDS tape.
Tape, not a round wire.
Usually a flat tape, yeah. And it's not just the superconductor. It's a sophisticated multi-layer composite structure, a high-tech sandwich.
Okay, break down the sandwich for us.
All right. At the bottom, you have a flexible metallic substrate, usually a strong nickel alloy like Hastelloy, that provides mechanical strength.
Makes sense. Need something tough.
Then, on top of that, you deposit a series of incredibly thin buffer layers. These are crucial. They act as a chemical barrier, preventing reactions between the substrate and the superconductor, and more importantly, they provide a crystallographic template.
A template?
Yeah, you grow these buffer layers so their own crystal structure is highly aligned, biaxially textured. Then, when you deposit the superconducting layer, the REBCO layer, which is itself only a few micrometers thick, it grows epitaxially following the template of the buffer layers.
So all the superconducting crystals line up perfectly.
Exactly. This creates a nearly single crystal-like film, eliminating those problematic grain boundaries, those weak links that plagued earlier efforts. This biaxial texture is the secret sauce for getting really high current density, high JC.
Wow, that sounds incredibly precise.
It is. Techniques like ion beam-assisted deposition, IEAD, or rolling-assisted biaxial texturing of substrates, rabbits, are used to create that template, combined with advanced deposition methods like MOCVD for the REBCO layer itself. It's material science magic, really, allowing kilometer-long tapes to be manufactured.
And the final layer?
Usually a stabilizer layer on top, often copper or sometimes silver. This doesn't help the superconductivity directly, but it provides protection. If a section of the superconductor accidentally quenches, goes resistive,
right,
the current can safely shunt through the copper layer temporarily, preventing the delicate HTS film from burning out. It also helps stabilize the tape thermally.
That is seriously clever engineering, but I imagine making kilometer-long, multi-layer, atomically precise tape isn't cheap.
You imagine correctly. This complex multi-step manufacturing makes 2G HTS tapes significantly more expensive than, say, conventional copper wire. That's been the major hurdle for widespread adoption.
So the economic question is really, does the amazing performance carrying much more current zero loss justify that high initial cost?
That's exactly it. For certain high-value applications, the answer is increasingly yes. But for broader markets, like power transmission, the relentless focus in the industry is on improving manufacturing, scaling up production, and driving down the cost per unit of performance, usually measured in cost per kilo-ampere meter.
And what about keeping it cold? You mentioned liquid nitrogen is easier, but still.
Right, cryogenics is still a critical part of the package. While liquid nitrogen is much cheaper and more manageable than liquid helium, maintaining stable low temperatures, especially for large-scale applications like long power cables or big magnets, requires sophisticated systems.
Like what?
You need advanced vacuum insulation, often called super insulation, multiple layers of reflective material in a vacuum, and you need efficient, reliable closed-cycle cryocoolers, essentially specialized refrigerators, to maintain the operating temperature, typically somewhere between, say, 30K and 77K, depending on the specific HTS material and application.
Does the cooling system eat up all the energy saved by the superconductor?
That's a key consideration. The refrigeration power is definitely a parasitic loss. But in most well-designed HTS applications, the energy saved by eliminating resistive losses in the superconductor itself far outweighs the energy needed to run the cryocoolers. The net efficiency gain can be substantial.
Okay, so the tech is challenging but developing. Let's talk about the payoff. Where are these transformative technologies actually showing up, or where are they headed? The grid, for instance.
The electrical grid is a huge potential area. HTS power cables are a prime example, because they can carry 5 to 10 times more current than a copper cable of the same size.
Wow, 5 to 10 times.
Yeah, it means you can transmit much more power through existing underground ducts in crowded cities, avoiding the massive cost and disruption of digging new trenches. Plus, you eliminate the 5 to 10% of energy that's typically lost as heat in conventional transmission and distribution lines. That's a huge energy saving.
Are these actually being used?
Yes, there have been several successful demonstration projects and even some commercial installations. The Ampasti project in Essen, Germany, replaced a conventional high-voltage cable with an HTS cable in the city center. There was the Resilient Electric Grid, or RE, project in Chicago connecting substations. These projects prove the technology works in real-world grid conditions.
What else for the grid?
Fault current limiters, FCLs. These are really neat devices. HTS materials offer a unique way to protect the grid from damaging power surges, like those from lightning strikes or short circuits.
How do they work?
Under normal operation, the HTS element in the FCL has zero resistance. Lets power flow freely. But if a huge surge of current comes through a fault current, the HTS material instantly quenches.
Goes resistive.
Exactly. It rapidly switches to its high-resistance normal state, which naturally limits the surge current, acting like a super-fast, self-healing fuse. This protects expensive downstream equipment like transformers from damage. They react much faster than conventional circuit breakers.
Very cool. What about magnets? You mentioned MRI and accelerator.
High-field magnets are another area where HTS really shines, because they can operate at higher temperatures and tolerate much higher magnetic fields than traditional low-temperature superconductors, LTS.
So for MRI?
The big hope is for helium-free MRI systems. Current MRI magnets use LTS wires and need baths of expensive liquid helium. HTS magnets could potentially operate around, say, 40-50 Kelvin, cooled by compact cryocoolers instead.
No liquid helium needed.
Potentially, yes. This could lead to smaller, lighter, maybe cheaper MRI machines, which could make MRI diagnostics much more accessible, especially in places that currently lack the infrastructure for liquid helium. HTS is also enabling research NMR spectrometers to push beyond 1 gigahertz field strengths, opening new windows for molecular analysis.
And particle accelerators, like the LHC.
Absolutely essential for the future. Next-generation colliders, aiming for much higher collision energies, will require magnetic fields stronger than what LTS magnets can reliably produce, maybe above 13 or 15 Tesla. HTS is the enabling technology there.
Are they using HTS at CERN now?
They are, actually. Not yet for the main bending magnets, but HTS current leads are used in the LHC. These carry the huge currents from the room temperature power supplies down into the cryogenic magnets, and using HTS significantly reduces the heat leaking into the cold parts, saving on cooling power. Future upgrades and designs definitely envision using HTS, perhaps in hybrid HTS-LTS magnet designs.
And you mentioned fusion energy. That seems like a huge one.
It's seen by many in the fusion community as a potential game changer, particularly for magnetic confinement fusion, like tokamaks.
Oh, so?
The strength of the magnetic field needed to confine the superhot plasma is a key factor in the size and cost of a fusion reactor. HTS wires can carry incredibly high currents, even in strong magnetic fields. This allows you to design much more powerful magnets, or perhaps more importantly, much more compact magnets that produce the same field strength.
Smaller magnets mean smaller reactors.
Potentially, yes. Companies like Commonwealth Fusion Systems, working with MIT, are banking on HTS magnets to enable smaller, potentially faster to build, and maybe lower-cost fusion power plants compared to designs based on traditional LTS magnets. It could significantly accelerate the timeline for commercial fusion energy, though many challenges remain, of course.
Okay, grid, magnets. What about transport? Maglev trains.
Maglev trains, exactly. That's another classic futuristic application. Japan's SC Maglev, the one that hit over 600 kilometers per hour,
Yeah, crazy fast.
uses powerful superconducting magnets for what's called electrodynamic suspension, EDS. The moving magnets on the train induce currents in coils on the guideway, creating forces that both levitate and propel the train.
So HTS makes that better how?
Well, current SC Maglev uses LTS magnets, requiring liquid helium. Using HTS magnets operating with simpler liquid nitrogen cooling or cryocoolers could potentially make the onboard magnet systems lighter, more robust, and critically cheaper to build and operate. It might make this kind of ultra-high-speed travel more economically feasible for wider deployment.
Fascinating. Okay, looking even further ahead. The ultimate dream, right? The thing everyone asks about. Room temperature superconductivity, RTS.
Ah, yes, the Holy Grail. It's captured the imagination for decades, a material that superconducts at everyday ambient temperatures, with no need for any cooling.
The implications would be just immense.
Almost unimaginable. A completely lossless energy grid worldwide. Ubiquitous magnetic levitation for transport. Revolutionized computing with superconducting circuits generating no heat. It would change everything.
And those high-pressure hydrides you mentioned, hitting 260 Kelvin, they show it's not impossible, right?
Exactly. LIARO and similar superhydrates provide that crucial proof of principle. They demonstrate that physics doesn't actually forbid superconductivity near room temperature.
Yeah.
The mechanism, even if it's conventional BCS, can get you there. The catch, of course, is the pressure.
Yeah, 1.5 million atmospheres isn't practical.
Not even remotely, no. So the real hunt, the intense, sometimes fraught search, is for an ambient pressure room temperature superconductor.
And that quest has been controversial.
That's putting it mildly. The field has been, well, rocked several times in recent years by really high-profile claims of ambient pressure RTS. These generated enormous initial excitement, global headlines.
I remember seeing some of those.
But they were subsequently met with widespread skepticism from the scientific community because other labs couldn't reproduce the results. And in some prominent cases, the original papers were ultimately retracted due to serious questions about data integrity or interpretation.
You're talking about that lutetium hydride claim from 2023, LK99 before that.
Precisely. The nitrogen-doped lutetium hydride paper claiming superconductivity up to almost room temperature caused a massive stir. But the lack of reproducibility and concerns raised about the data eventually led to its retraction. These episodes, unfortunately, serve as pretty stark case studies in, well, scientific sociology. They highlight that intense pressure to publish ground-breaking results, but also the absolute paramount importance of rigorous methods, transparency, and reproducibility in science.
So where does that leave the quest? Is it still going?
Oh, absolutely. Despite the setbacks and the controversies, the quest continues with immense vigor. Many theorists are still convinced, based on calculations, that ambient pressure RTS might be possible, perhaps through unconventional mechanisms we don't fully understand yet.
So looking beyond hydrides and cuprates.
Yes, researchers are exploring entirely new material systems, different oxides, the nickelates we mentioned, maybe materials without any copper at all. They're delving deeper into novel pairing mechanisms, like the role of electronic pneumaticity or other forms of electronic order. And advanced computational materials discovery using AI and machine learning is playing an increasingly important role in suggesting new candidate materials to synthesize and test.
But with more caution now, presumably.
One hopes so. The path forward really has to be paved with meticulous, transparent, and rigorously verified experimental work. The potential prize is enormous, but credibility requires extraordinary evidence.
Okay, so wrapping this all up, We've really journeyed from this completely unexpected serendipitous discovery that just shattered the old scientific paradigms
Totally out of the blue.
through the incredibly complex quantum physics trying to explain these mysterious materials, and then into the really clever, intricate engineering challenges involved in actually making them useful. High temperature superconductivity, it's this amazing intersection of fundamental science, materials innovation, and practical application, constantly pushing boundaries.
Indeed. And what's clear is that HTS materials, they're not just lab curiosities anymore. They're actively transitioning into becoming key enabling components in genuinely transformative technologies.
Yeah.
It's still a balancing act, that revolutionary potential versus the very real practical hurdles of cost and manufacturing. But the progress is undeniable.
So what does all this mean for you listening in? Well, while that dream of a true, practical, walk-around, room temperature superconductor, that still seems to be on the horizon, maybe consider this. What other scientific limits, what other barriers do we unknowingly just accept today as unbreakable? And what surprising, maybe counterintuitive idea, like looking for superconductivity in an insulator, might be just around the corner ready to shatter them all over again?